Hey everyone, it's John Oden here on the development team at Boson Software. We are back with the fifth presentation in our series entitled Subnetting Demystified. And in this presentation, we're going to take up this topic of CIDR notation. Well, let's talk about what is CIDR notation. First of all, CIDR, C-I-D-R, is an acronym that stands for Classless Interdomain Routing. Now, we're not going to take on the entire topic of classless interdomain routing, but we are going to talk about the notation, or the way that we can write IP addresses and network addresses that allows us to depart from this world of classful addressing that we learned about in our fourth presentation and start to explore this new world of classless networking, wherein the dividing line between networks and hosts could be at any point along the 32-bit value of an IP address that we choose to put it. So let's go ahead and get into that. CIDR notation, classless interdomain routing notation, slash notation, variable length subnet masking. These are all terms that refer to the same or similar idea that we need to get to a place where we are not constrained to putting the dividing line between the network number and the host number at an even octet boundary. Before we get too far along with that, let's do a little bit of a review. You can look and see here that on the whiteboard I have written an IP address. Now, I've written it in binary format, and this is typically not the format that we use when we are communicating human to human regarding IP addresses, but this is the format that the data structures in your computers, routers, and other devices that use IP deal with an IP address. You can see that it is a 32-bit binary value, and we typically chop it up into 8-bit chunks that we call octets, and I've written them here on the whiteboard with a little bit of space in between. So the first thing that I would like to do is to have you pause the video and convert this binary IP address into its dotted decimal equivalent. So go ahead and hit pause on your video, take pencil and paper, and see if you can go ahead and do that conversion. And then come back and let's resume, and then we'll go through the conversion together so you can check your work. Okay, let's work through this conversion together. The first thing that I'm going to do is to write the bit weights of each of the positions in the first octet up here on the whiteboard, just to give us a little bit of a visual hint. You'll recall from our previous presentation that each of these bits carries a weight starting with the most significant bit in the leftmost position of each of these octets, which carries a bit weight of 128, and then the next bit to the right of that is 64 and 32 and 16, 8, 4, 2, and 1. So to convert from a binary value to a decimal value, it's a simple matter of just adding up the bit weights. So if we examine this value, we can see that the first bit with a weight of 128 is set to a 1, and the next bit with a weight of 64 is also set to a 1. So to convert from binary to decimal, we just add those together. So we take 128 and 64, and we take the sum of those two values, and what do we get? We get 192. So the decimal value of our first octet is 192. Now, if we look over at the next octet, I won't write the bit weights out all over again. We can just kind of borrow the ones that I've already written. You can see that the first bit with a weight of 128 is set to a 1. The next bit is still a 0. And then the bit after that with a weight of 32 is set to a 1. And then we've got another bit a little bit further down the octet that's set to 1. And what is that? That's going to be 1, 2, 4, and the bit weight for that guy is going to be 8. So all we've got to do is add them up. We take 128 from here. This one is 32, so we sum those and get 160. And this one right here is 8. I'm counting from the right back to the left this time. 1, 2, 4, 8. So we've got 168 right here. In the third octet, the first most significant bit is set to 0. So we've got the 64's position is set to 1. The 32's position is set to 1. So if we take 64 and 32 and add those together, what do we get? We get 96. And this bit is in the 1, 2, 4 position. So we've got 96 plus 4, and that gives us a value of 100. And then in the last one, that one's easy. 1 is 1. So The decimal equivalent of this binary format that we see here is 192.168.100.1. Now keep in mind, we're still reviewing here. We're still thinking in classful networking terms. So remember from our previous presentations that every 32-bit IPv4 address contains two pieces of information. The first piece of information is what is the identification number for the host to which this IP address is assigned, and also what is the identification for the network to which this host belongs. So if we're dealing with classful addressing, and we still are here in this example, we learned in our previous presentations that the IP address itself, that's really all we need in the classful world, because we can examine these first 3 bits of the first octet and determine whether we're dealing with a Class A address, a Class B address, or a Class C address. And depending on which one we have, we know that the dividing line between network number and host number will occur either between the first and second, between the second and third, or between the third and fourth octets. Now, if we look right here, we remember from our previous presentations that Class C addresses begin with 110. So if we examine the first octet, the first 3 bits, and if we see 110, we know that this is going to be a Class C address, and that tells us that the dividing line between network and host is going to be right here. So these first 3 octets are network, and this last octet is host. In the early days of IP networking, once we assigned the IP address to the network node, we were done, because the IP software that ran on that node could then use classful networking rules to surmise that this is host number 1 on the 192.168.100 network. Now, we are not constrained by that today. We can actually put this dividing line between network and host anywhere along this path that we want, and that's the topic that we're starting to ease our way into here. So I'm going to give you an example and show you, though, that even today, modern computing platforms can still do classful networking. I'm going to bring over the properties dialog box for the Ethernet adapter on my computer here, and I'm going to scroll down to the IPv4 item, and I'm going to open its properties dialog, and you can see that my computer, like most, is configured to obtain an IP address automatically from a DHCP server. But just to show you that modern computers can still do classful networking and still do classful networking, I'm going to elect to enter my IP address manually, and I'm going to put in the IP address that we're using here in our example, 192.168.100.1. Now watch what happens when I move my cursor from the last octet of the IP address field down into the subnet mask field. Notice that it already knows, or it presumes, that the dividing line between network and host should occur right here. 255, 255, 255, 0. Imagine all of those 255s converted to ones, and the ones identify where the ones stop. That's where the network stops and the host number starts. So even today, computers still understand classful networking. Now, we're not limited to that. With this subnet mask value, we can change that around and put the dividing line between network and host anywhere we want it, and that's the topic that we're easing into here in this discussion. So in modern computing platforms, and modern is a relative term, I'm talking about anything within the last several decades actually, not only do we enter an IP address, but we also enter a subnet mask. Now we can accept the default mask, which we saw in that example when I had my IP properties of my Ethernet adapter displayed here, and it surmised that the default mask for this IP address in the classful networking world should have been 255, 255, 255, 0. And you can see now that I've done the binary conversion on the mask as well, and that's pretty easy. These 255s simply equal all ones. If we were to take 128, 64, 32, 16, 8, 4, 2, and 1, and add all that together, we get 255. So 255 in the first octet, and the second and the third gives us 24 bits of ones, and then the last 8 bits of zeros is indicating the host portion of this IP address, and there's the dividing line right there. So what if we wanted to express this idea using CIDR notation? Well, here's how we do it. 192.168.100.1/24. And that's all there is to it. That's all there is to CIDR notation. It's simply a way to, rather than use a subnet mask like 255, 255, 255, 0, we can simply write out the IP address or the network address and then put a slash and then specify the number of bits counting from the left that represent the network portion of the address. We can also call that the network prefix. So what this means here is that the first 24 bits of this IP address are network, and the last remaining bits, the last 8 bits, are host, and the dividing line is right there. So this and all of this mean exactly the same thing, just two different ways to express the same idea. Now, I've changed the scenario here just a little bit. Notice that in the last octet, instead of having a host number of 1, I've changed it to a host number of 41. And I've just gone in and used my marker here to flip these bits from 0 to 1, so we can see that this is the bit in the 32 position, so we've got 32 here. This is the bit in the 8 position, so 32 and 8, that's 40, plus this last bit here is 41. So that gives us 192.168.100.41. Now, let's say that you were to open up the properties of your network adapter and go look at your IPv4 configuration, just like I did before, and you were to see something like this. Let's say we saw an IP address of 192.168.100.41 and a subnet mask of 255.255.255.192. Now, what does that mean? That's a little different. In this scenario, we're not dividing the IP address between network and host on an even octet boundary. So the way to pull back the curtain on this and see what's really going on is to write that subnet mask up in binary format. So let's do that now. I did the first 3 octets because that's easy. Decimal 255 is binary 11111111, and that's true all the way across the first 3 octets. But what about this 4th octet? We've got 192. So how do we represent that in binary for the last octet of the subnet mask? Well, we do like we've always done. We just add up the bit weights. Remember, this first position here in the last octet is 128, and the next is 64. So if we add 128 and 64 together, there's our 192, and then we just represent the remaining 6 bits with zeros. And those 6 zeros represent the fact that in this addressing scenario, we've got 6 bits that remain for host addressing. How many hosts could we have? Well, we could take 2 to the 6th power, and that's going to be 64 possible addresses. But remember, we've always got, when we're talking about host addresses, we've always got 2 special cases. We've got the special case where all of the host bits are 0, and that's how we identify the network, by setting all of the host bits to 0. And then we've got the directed broadcast address where all the host bits are set to 1. So in this situation here, where we have 6 bits for host addressing, we have 2 to the 6th equals 64, minus those 2 special cases gives us 62 actual usable host addresses in this configuration. So how do we write this in CIDR notation? Well, here we go. 192.168.100.41, that's the entire IP address. And let's think about now how many bits are network and how many bits are host. Well, we've said that 6 bits, these 6 bits that are represented by the zeros portion of the mask, that's for host addressing, and the remaining bits are for network addressing. So we've got 3 full octets, that's 3 times 8 is 24, 25, 26. So we could just write /26. And that's how we could represent that particular IP address and mask using CIDR notation. That's for the host. Now, what if we wanted to specify the whole network? Well, we just look at what we have. We've got 192, 168, 100 in the first 3 octets. That part's easy. And then what about the network portion of the last octet? Well, we've got 2 zeros right here, so that's going to be 0/26. So the entire network that could contain these 62 hosts, we would refer to that as 192.168.100.0 network /26, and that would be the CIDR notation for the network, and this is the CIDR notation for the host. As you continue to develop your IP addressing and subnetting skills, it's important to be able to take an IP address or a network address in either format and convert it to the other. So maybe you're given an IP address in decimal notation with a decimal mask. You need to easily be able to convert that to CIDR notation, or maybe you're given something in CIDR notation, you need to be able to quickly and easily convert that into the decimal mask equivalent. So what I'm going to do is to put up some practice exercises on the whiteboard, and I'm going to have you pause your video and work through those using the techniques that I've shown you here, and then after we'll come back and go through them together and check our work. Well, okay, now that you've seen the process in practice, this idea of CIDR notation and how we can look at either an IP address and decimal mask and convert it to CIDR or go back the other way, I've got 3 examples here on the whiteboard that I would like for you to pause the video. And here's the first example up here, 198.51.100.81/27. Then we've got another one in CIDR notation, 172.16.180.7/23. So what I would like for you to do with each of these is to go out to the side, just take a pencil and paper and do this, and write out the decimal subnet mask that would be the equivalent of a /27, and also write out the decimal subnet mask that would be the equivalent of a /23. And in this last example, I've given you an IP address and a subnet mask already in decimal format, and I would like for you to convert this one back into CIDR notation. It'll be 192.168.88.116/something. So that will be for you to figure out what the number after the slash should be in this last example. So go ahead and pause the video and work through these 3 examples, and when we come back we'll go through them together. Okay, let's take the first one. Now I've already written out the IP address, and it's just the IP address that you see, 198.51.181. Now the question is, what is the decimal equivalent mask of a /27 CIDR? Well, we know that /24 is 255, 255, 255, right? Because each of those octets represents 8 bits. So we've got 1, 2, 3 octets. 3 times 8 is 24. So a /24 would look like this: 255.255.255. But we're not done yet, because this is not a .0. A /24 would be a .0. We've got a /27. So the mask has got to extend 3 bits into that last octet. So to figure out this last number of our mask, we simply add up the bit weights of the first 3 most significant bits going from left to right of this last octet. Now, I'm going to start getting you into the habit of doing more of this in your head without having to write it out every time. So imagine the last 8 bits of the 4th octet, and what are the bit weights of each of them. The most significant one over on the left is 128, and then 64, 32, 16, 8, 4, 2, and 1. So as we go through there, we just add them up. We've got 3 bits. We've already got a /24 accounted for here, so we've got to take the bit weights of the first 3 bit positions in this last octet and add them together, and that'll give us the last decimal value for our mask. So we take 128, 64, 32, and add them up. What do we get? Well, we've already seen that 128 and 64 is 192, so we add 32 to that, and we get what? 224. So there is the decimal equivalent mask of a /27. Okay, let's take the next one and work through that. I've written the IP address 172.16.180.7 out there, and we can see that we are given a CIDR notation of a /23. So our challenge is to figure out what is the decimal equivalent mask to a /23. Well, we know that a /16 is going to be 255.255. So let's go ahead and write up there what we know already, 255.255. So this one gets a little more interesting. Before, we saw that all of the action was in the 4th octet. Well, here we're concerned with the 3rd octet. So anytime you're breaking down a problem like this, it's always useful to first figure out what is the interesting octet. Well, if you're working with a /27, the interesting octet, or that's the interesting octet is the octet within which the dividing line between network and hosts fall. So if we got a 27, we know that it's going to be over here past 24, so it's going to be somewhere in the 4th octet. If we've got a /23, we know that the dividing line is not going to fall in the 4th octet because that would be a 24 or greater. We know that it's not a 16, so it's got to be somewhere in this 3rd octet. So that's where we're going to be focusing our attention. So how do we solve this problem? Well, we've already accounted for the first 16 of those 23 bits because 255.255, that's a /16. Well, we've got a /23 to deal with, so if we take 23 bits and subtract from that 7 bits that we've got to account for, then we can just add up the bit weights of the first 7 positions of this 3rd octet, just like we did in the 4th octet of our previous example. So what's that going to be? Well, we take 128 and 64 and 32 and 16 and 8 and 4 and 2 and add all those together, and what value do we get? Okay, you've probably already worked through this, and let me get you in the habit of thinking in terms of a shortcut. If we know that if we had all of those bits set to 1, the decimal value is 255. So we're 1 less than that. So 1 less than 255 is 254. So you could either take 128 and 64 and 32, 16, 8, 4, and 2 and add those all up together and get 254. Or since we're just backing up 1 bit, you could take 255 and subtract that and just take away that last bit and you would get 254. So the decimal mask equivalent of a /23 is 255.255.254.0. So in this last example, we're asked to do the conversion the other way. We're given the decimal mask. So given this decimal mask, what would the CIDR notation, what would the slash number be for 192.168.88.16 with a decimal mask of 255, 255, 255.240? Well, let's think through that. First of all, let's identify the interesting octet. It's going to be this last octet right here because 255, 255, 255, that would be a /24. So we're going to be several bits beyond 24 to add up to 240. So how do we do that? Well, again, just take the bit weights of the starting with the most significant bit going toward the least significant bit of that last octet and just add them up until you get 240. So I'm not going to draw these in decimal out for the first 3 because we know they're all 1, so I'm just going to write them in decimal. And this last one, I'm going to write it in binary. So there's a 1. That's the 128 position. There's another 1. That is the 64's position. And there is another 1, and there is the 32's position. And then there is another 1, and there's the 16's position. So you recall from up here, if we added 128, 64, and 32, we got 224. Well, if we take 224 and add 16 to that, then we get 240. So that's what that last octet of the mask would look like if we wrote it out in decimal. 128 plus 64 plus 32 plus 16, that's 240. That's 4 bits, 1, 2, 3, 4. So if we were to represent that in slash notation, that would be what? That would be a /128 We've got 24 bits here already, plus these 1, 2, 3, 4 more, so that's going to be a /28. Okay, that about wraps it up for presentation number 5 in our series on subnetting. Thanks for taking your time to follow along with this. And in our next presentation, this will be number 6, we're actually going to get into subnetting. Everything that we've done in these first few presentations, these first 5, is to lay the groundwork, to give you the basics of how IP addresses work, how do classful networks work. Now we've seen how classless networks work, where we can put that dividing line anywhere we want to. And we're going to take that idea and then develop it into the whole idea of subnetting. Why do we want to subnet? What reason is there for subnetting in the first place, and how do we do it? So tune in to our next presentation. This will be presentation number 6, where we'll get into subnetting. Thank you.